Welcome back to G-Fun Facts Online. Today, we are going deep into one of the most violent and confusing events ever recorded in the history of astrophysics. If you think you know how stars die, you might need to rewrite your mental textbooks, because on August 18, 2025, the universe showed us something that should NT have been possible. We are talking about the day the sky exploded twice. We are talking about the Superkilonova. To really understand why this event, catalogued as AT2025 ULS, has shaken the scientific community to its core, we have to start with the standard model of stellar death. For decades, astronomers believed that the heavy and the dense died in two very distinct ways. Option 1 is the supernova. A massive star runs out of fuel, its core collapses, and it detonates. This is a lonely death. It happens to a single star, and it results in a singular, blinding flash. Option 2 is the kilonova. This is a partnership. It requires two ancient neutron stars, the crushed cores of dead suns, spiraling around each other for millions or billions of years until they finally collide. This merger rips through the fabric of space-time and scatters heavy metals like gold and platinum across the cosmos. These were the two separate chapters in the book of astrophysics. You have the lonely explosion, or the binary merger, but on that morning in August 2025, those chapters got smashed together. Sensors buried deep within the Earth, and telescopes on mountain peaks detected a signal that combined both. It was a star that didn't just die, it tore itself apart to build its own executioners, creating a kilonova inside a supernova. Let's break down exactly what happened, because the details are absolutely fascinating. It started at the Laser Interferometer Gravitational Wave Observatory, or LIGO. The facility had been quiet until 9:42 Coordinated Universal Time, when the automated alert system triggered. They picked up a gravitational wave signal, labeled GW250818. This signal swept through detectors in Washington, Louisiana, and Italy. It was a classic chirp, the rising frequency sound that indicates two massive objects spiraling into each other and merging. But when the computers crunched the numbers to estimate the mass of these objects, the room went silent. Here is the problem. Physics tells us that neutron stars generally have a mass between 1.1 and 2.3 times that of our Sun. If they are lighter than that, gravity isn't strong enough to crush protons and electrons into neutrons, so you get a white dwarf. If they are heavier, they collapse into a black hole. But the signal from GW250818 broke these rules. One of the objects in the merger weighed in at just 0.7 solar masses. That is physically impossible under standard models. As Dr. Elena Rossi from the Institute for Advanced Study put it, it was like finding a fully grown elephant that weighed as little as a golden retriever. They thought it was a glitch, maybe a truck driving by or a minor earthquake. But the signal was clean. It was real. While the gravitational physicists were scratching their heads over this impossible object, optical astronomers turned their telescopes to the constellation Eridanus, about 1.3 billion light-years away. The Zwicky Transient Facility in California spotted a new point of light. Now usually, a supernova starts blue and hot, then slowly fades. But this object was red. Deep, angry red. And it was fading fast. This is the classic signature of a kilonova. That red color comes from heavy elements like lanthanides and actinides, things like gold and uranium, blocking the blue light. So at first, everyone thought, okay, we have just seen another standard neutron star merger, like the famous one in 2017. But the universe had a twist waiting. 3 days later, just when the object should have faded into blackness, it stopped dimming. It began to brighten again. And not only did it get brighter, the color shifted from that heavy metal red to a scorching, hydrogen-rich blue. The dead star was exploding again. It was like watching a movie where the credits had already rolled, and suddenly the main character stands up and starts a whole new plot. The timeline was backwards. We saw the merger of two neutron stars first, and then we saw the explosion of a massive star. But you can't merge two neutron stars until the star that made them has already died. Yet here, they seem to be happening on top of each other. This paradox led to the theory of the superkilonova. To understand how this works, we have to look at the mechanism called rotational fission. The star that caused this, likely a massive Wolf-Rayet star, wasn't just sitting there, it was spinning. And I mean spinning at a breakneck speed. Imagine a figure skater spinning so fast that the centrifugal force is ripping them apart. When the iron core of this giant star collapsed, it didn't crunch down into a single ball like usual. The spin was so intense that the core stretched out into a bar shape and then snapped in two. Instead of one standard neutron star, the collapsing core split into two smaller, sub-solar mass protoneutron stars. This explains the weird 0.7 solar mass reading. These two baby neutron stars were born in a frantic, screaming orbit around each other, separated by mere kilometers, trapped in a death spiral from the moment of their birth. Because they were so close, They emitted gravitational waves of incredible intensity and merged less than a few minutes after being born. This happened deep inside the belly of the star, before the outer layers even knew the core had collapsed. So the sequence of events was terrifyingly fast. First, the core collapse. Second, the fission into two objects. Third, the merger, the kilonova, releasing a burst of neutrons and gamma rays inside the star. And fourth, the detonation. The energy from that merger slammed into the falling layers of the star, boosting the standard supernova explosion. That explains the signals. The gravitational waves came from the internal core merger. The initial red flash was the kilonova engine breaking through the surface. The blue brightening was the main supernova finally lighting up. Now, why does this matter to you? It matters because of the gold ring on your finger or the components in your smartphone. For a long time, we had a crisis in astrophysics called the R-process crisis. We didn't know where the heaviest elements in the universe came from. The Big Bang gave us hydrogen and helium. Normal stars make carbon and oxygen. Supernovae make iron. But for gold, platinum, and uranium, you need a flood of neutrons, the rapid neutron capture process. We thought standard neutron star mergers were the answer, but when we did the math, they were too rare. There just aren't enough of them to account for all the gold in the Milky Way. The Superkilonova solves this. If a single massive star can undergo core fission and produce a merger all by itself, without needing a binary companion, these events could be much more common. A superkilonova is essentially an R-process bomb. Because the merger happens inside the exploding star, the neutron-rich debris gets mixed into the supernova shell and spreads efficiently across the galaxy. The spectrum of AT 2025 ULs showed signatures of strontium, tellurium, and even indications of californium. It suggests that these events are the true factories of the heavy elements. It is very likely that the majority of the precious metals in the Earth's crust were not born from the lonely wandering of binary stars, but from these violent, solitary suicides of rotating giants. There is one final piece to this puzzle. What gets left behind? When those two subsolar neutron stars merged, their combined mass was roughly 1.4 to 1.8 solar masses. That is actually quite light for a neutron star, but because of the violent mixing during the merger, the magnetic field would be amplified to ungodly levels. The result is likely a magnetar, a neutron star with a magnetic field 1 trillion times stronger than Earth's, spinning hundreds of times per second. Astronomers believe that AT 2025 ULs has birthed a new magnetar, and radio telescopes are already listening for the first chirps from this newborn monster. This discovery, the Superkilonova, is comparable to finding the first black hole. It connects gamma-ray bursts, magnetars, and the origin of elements into one cohesive picture. It reminds us that nature doesn't care about our clean categorizations. We like to put stars in boxes. Supernova here, kilonova there. But the universe is messy. It smashes the boxes together. The energy released by this event was colossal, but its true power lies in what it taught us. That the heavy atoms in our bodies, the iodine in our thyroids, the gold in our electronics, might have been forged in a rare, violent dance of twin cores inside a dying giant. As we speak, the shockwave from that explosion 1.3 billion light-years away is still expanding, creating a nebula that will one day form new stars, and perhaps new planets, unaware that their wealth came from the day the sky exploded twice. Thanks for listening to G Fun Facts Online, and we will catch you in the next deep dive.